Hello everyone. Today we'll be glossing over the generalized version of bolzano weirstrass theorem. It's quite an important theorem in the field of real analysis. Uh, so when the basic, when the elementary set of real numbers states that any sequence of a sequence of real numbers that is bounded above a bound that is bounded must have a subsequence that will converge. And the generalized version of the Bolzano versus theorem states that. First I have to define what is a bounded set in a space of Rn. Rn is a n-dimensional real space, real vector space. A set S and Rn is said to be bounded if it lies in some kind of ball, n ball. I will not define what is an n ball because I will define it later in a video that will be dedicated to what are balls. For okay, so for some r greater than 0 and some a in Rn, so that's basically a bounded set in Rn. Now the general theorem of Bolzano-Weierstrass theorem states that if a bounded set in Rn contains infinitely many points, be specific with this. I'm quite emphasizing the point that there are infinitely many points in that bounded set. So then there is at least one point in Rn which is an accumulation point of S. What is accumulation point is exactly limit synonymous to limit point in the real vector space, the R1. So there will be if a point in Rn or rather element in Rn is an accumulation point, then there exists a sequence of and there exists a sequence in Rn that converges to that point. So that's basically the whole idea, and I'll go through the proof. So the proof for R1 is simple. You could refer Bartle and Sherbert. It has a more rigorous treatment. A bit at the it has a more rigorous treatment than or it's kind of vague over here. I'm trying to say that Apostle treats it in a kind of the treatment in Apostle is quite vague, somewhat vague compared to Bartle and Sherbert. So I would suggest you to refer Bartle and Sherbert for the proof in the case of R1. So moving on to the next, we give a proof of Rn for the generalized case where n is greater than 1 by the extension of the ideas that we used for R1 there. So you could go through the proof for yourself for your own reference. I will not refer to the proof because that is kind of redundant. That will be treated in another video, separate video. Let's treat Rn right as of right now. So yeah, S is bounded, and so S must lie in some n ball, and therefore each entity in that n vector, each entity in that vector will lie between a and minus a. So that's because we know that it lies in some kind of n ball. So each and every entity must satisfy this inequality. So let J1 be denote the Cartesian product I1 of 1, I2 of 1, cross up to In of 1, where this is that is the set of all points, x1 up to xn, where xk belongs to ik of 1, and where each ik of 1 is a one-dimensional interval, where we're just restating the above thing in a quite fancy way. So don't get deluded by this kind of wordings. So let's move on. So each interval can be then bisected to form two intervals, uh, which can be represented by these two entities, defined by the inequalities. I mean, again, we were just bisecting each of the subintervals. Not the sub, each of the subintervals into another it's a bifurcation of each sub-interval into two intervals where the new xk will lie between 0 and minus a, and the xk belonging to the other sub-interval will lie between 0 and a. It's obvious. So next we'll consider about all possible Cartesian products of the form of these kind. I mean, I hope you are clear with how these intervals are defined. I mean, I'm just glossing over the facts because I have a time constraint. I cannot show you rigorously why and how these intervals are defined and bifurcated, but just accept these facts and go along with the proof with me. I may be wrong at some. Please rectify me in the comment section. So, so next, after considering each possible Cartesian products of the form of these kind, where each ki is one or two, obviously, because it is bifurcated, right? So there are exactly 2 to the power n such products, and of course, each product is an n-dimensional interval, right? So I mean, yeah, I one of 1 into it's a combination of all those rather a combination of all those kinds of intervals. I mean, you have to just find the, you have to find the correct I mean, you have to select an interval out of all those combinations. So the union of these two intervals as the original interval j1, which is obvious. Of course, it has to be the original interval, because you could easily show that every interval in this lies in j1 and vice versa, so which contains s. Um, so hence at least one of the two n intervals must contain infinitely many. Why? Because if on the contrary, if all the intervals contain finitely many points, then the union must have finitely many points. So we just contradict our hypothesis. So at least one of the two intervals and A must contain infinitely many points of S. So one of those we denote by J2. Now you must be getting along with the proof of what is the kind of approach we are dealing with. It is the same kind of approach that we dealt with R1, the specific case of where n is equal to R, where n was 1. It was a single dimensional real vector space. Now we are dealing with a n-dimensional real vector space. So the overall process is similar, and moving along with this, we will again end up with these kind of intervals. Then this just goes on and on and on, unless you will just arrive at an you will just absorb that the length of the interval decreases exponentially. So hence for a fixed k, the supremum of all left endpoints must therefore equal to the infimum of all right endpoints. They must converge, because you know the concept over here. It is decreasing exponentially. So, and by the characterization of intervals, or it must it must have a common value which we denote by tk. We now assert that the point t defined by t1, t2 up to tn is an accumulation point of evidence. To verify this, you could go through this section, and that's it. That's the bolzano theorem. Uh, that's what basically the bolzano theorem wants to convey. Thank you, everyone.